Hello and welcome to this tutorial on using vectors in game development in Crayta. So in this tutorial I'm going to talk a little bit about what vectors are and why and how you might want to use them in your games. So a vector is essentially a list of numbers and we use vectors all the time in games development to talk about the position of items in our game worlds. So I've got a couple of locators here and I've got a locator called origin. And all of these locators have a vector which is called position. So position of these, of each of these, is a vector. The list of numbers here, this one, and this one, describe the position of this object in the game. So this first one is its x position. So that's the position on this red direction here. The red arrow points in a direction. And you can see if I move this locator in the direction it's pointing, that number in the position vector here, the x number, increases if I move it in the direction it's pointing. If I move it in the direction it's not pointing, or opposite to that, it will decrease. And in fact, it can go into minus numbers. So we know that that first number determines the position of that locator on this axis here, this x-axis. The second number is the y value, and that determines the position of this vector, the position of this locator on this axis. So the vector is called position, and the first number of our position vector is the x-axis. The second number is the y-axis, which is this green arrow, and the final one is the z-axis, which is this direction here. For the majority of this tutorial, I'm going to be looking at this stuff in 2 dimensions, but that is only temporary because essentially everything in this game world is in 3 dimensions, and everything will apply to those the 3 dimensions anyway. I'm just using the 2 dimensions because it's a little bit easier for us to visualize that, and we're doing the whole run before you can walk thing. So a vector can tell us, can describe the position of a locator in our game world. And in fact, it can describe the position of anything in our game world. If I put a rock there, notice it's still got the position vector and it still describes the position of that. Now, if a vector can also describe the relationship between 2 points. So it can, those 3 numbers can be the x, y, and z of the position itself, but they could also be the relationship between those. So the difference, the distance in x, the distance in y, and the distance in z between those 2 points. So let's do a bit of coding to show you what I mean. So I've got a script attached to the origin here called Vectors Explained. And in the script, I've got 2 entities, one's A, one's B. So they refer to A and B here, are 2 points, locators, in the game world. And what I'm doing is I'm getting hold of their positions and storing them in A and B. So A refers to the position vector of locator A. So this 200, 200, 0 is now being stored in that A there. So that is a vector. The same with B. So B is getting the position of point B, which is 200, 500, 0, and storing those in there. And we can print out vector A by doing literally just printing that value. And if I run the game, you can see it says position of A as a vector 200, 200, 0, which is the same as 200, 200, 0. Now, what I was talking about was using a vector to describe the relationship between those 2 points. So the relationship between point A and point B. So to get hold of that, the long way round of doing it, to show you what's happening behind the scenes, is this. I'm going to call it vector AB because that is the vector which describes the relationship between A and B. So the line, vector AB is actually a line between these 2 points. So that line is going to be essentially create a new vector, and it's going to be b.x minus a.x for the x value, b dot y minus a dot y for the y value, and b dot z minus a dot z for the z value. So let's get this printing out, vector AB instead. And that will give us the vector which describes the line between these 2 points. So it's still 3 numbers, they're still x, y, and z, but now rather than being a position in the game world, they describe a line or a relationship between 2 points, which is essentially what a line is. So 0, 300, z is this line here. So let's just draw the line. Draw the line. So that line is that vector. So just to make that, hopefully that's clear. Now, why would we do that? What's the point in getting that vector there? Well, let's look at what we can do with that. Using the Lua API, we can actually get hold of the distance between 2 points now using that vector. Now, the old school way, or not the old school way, but the mathematical way of doing the distance between point A and point B would be, let's just do this like the verbose way so that we can look at, and then I can show you how to leverage the Lua API in order to do this simply. So the distance between A and B will be vector AB dot x times vector AB dot x plus vector AB dot y times. So you can see what we're doing. We're doing a squared plus, we're doing x, the distance in x squared, distance in y squared, and the distance in z squared. We're doing all of those added together, and we actually need to square root that. So we're using Pythagoras. This is Pythagoras' theorem that the hypotenuse is the of a right angle triangle essentially is equal to the sides of that right angle triangle squared and the square root of those. So that's using some Pythagoras, and we can get hold of that distance here. So let's output the vector AB and let's output distance AB, and lo and behold, distance AB is 300. That is because it is essentially the same as y, because that's the only distance between them. They're exactly the same x, they're exactly the same z, so the distance between them is all the difference there is on the y-axis. So let's just output, A and B as well. Let's talk about what that's doing. So A and B, there we go. So we've got A is the position x 200, y 200, z 0. B is the position x 200, y 500, z 0. So the line between them is determined by vector AB, which is x is 0, y is 300, z is 0. And so the distance between point A and point B is 300. Now that distance will work regardless of where these points are, and so will this vector. So if this point here went this side and moved over here, we can see that now vector AB looks very different, and distance AB also looks different. But notice, whilst vector AB has got x is 900, y is minus 637.5, it's still describing the line between those two. And notice that distance AB, regardless of whether it's behind that point or in front of that point or some other place in the world, that distance will always be positive because we're squaring everything and then we're square rooting. So we're always going to be a positive number for the distance. So that's great, and we can get the distance between 2 points, yay, and we can describe the line between 2 points, yay. But there's easier ways to do this because we're actually working in a really powerful game engine. So let's leverage that. So vector AB, rather than doing this complicated maths here, we can actually just do B minus A. And that will essentially get us vector AB. this distance, rather than doing this complicated Pythagoras theorem, we can actually leverage the API that knows already how to do those formulas. And that's literally going to be vector AB length. So that's the distance of whatever that vector is. And let's run the game, and you can see that the numbers are exactly the same. So we've just tested that the API works, and it does. Hooray! So there's some maths, and that's the start of these vectors. Now, what can we do with these? Let's have a think. So now that we know we can get hold of the distance between 2 points, let's add something to the game world. Let's add a robot to the game world. There. And we can actually get hold of the distance between the robot and the player. So we need a reference to the robot, which I'll put here. Rotobo. I'm going to call it Rotobo. Rotobo, the type is an entity. And then in our onTick, because we're going to check, actually let's just check it once at the beginning and then we'll check it every frame after that. So we're going to do get world, just get hold of the users, because there's only going to be me, but this is a way to make sure that it won't break. And it actually technically would work with more than one user. Get the user, and let's get the position of the user. So local user position equals user get player get position, and let's get robot position just by referring to the robot property rotobo get position. So we're basically building this vector AB, but we're using some real world things now. So this is going to be vector. So to get the vector between them, vector user robot equals the robot position minus the user position. And let's output that vector. Okay, so let's run the game, and that has not worked. That is because, let's just move that function to the onTick. Yes, because, oh, Rotobo I never filled Rotobo. Let's just rename that Rotobo. Just so that I don't get confused. Okay, so we're printing out a lot the vector between the user and the robot. And as I move around, you can see that that vector is changing. As I move closer, the numbers will get smaller. As I move further away, the numbers will get larger. Because the line between myself and the robot is getting smaller and bigger. We can see the distance between us using the same thing we used before. So we just get the length between player and Rotobo. At the moment it's 1593. If I move away, that number increases. As I get closer, it decreases. And it doesn't matter which direction the robot is to me, the distance will always be accurate. So that's a cool thing we can do with vectors. One thing we can use that for then is we can run a condition on that. We can say if the length is less than 500, then let's output. Let's just do like a proximity robot that says hello. So if you're close enough to the robot, says Rotobo. Hello, says Rotobo. So if you're close enough, then he'll say, or she'll say, or it'll say, hello. Let's get rid of that. There. Rotobo says hello. Now that I'm close. But we can do so much more with vectors. So that's like a simple thing. We can do a condition and we can check how close we are to something. But let's do something more interesting. Now that we have this vector, the relationship between those 2 points, we can use that to make the robot. Let's make the robot look at the player. Yes. Just put that in there. I think that works. Oh. It's not robot, it's Rotobo. Okay. Yeah, so, I mean, is the robot looking at me? Yeah. So the robot's now, no matter where I run, that's kind of creepy, admittedly. Just made a very, very creepy robot. But the robot will look at me. Cool. What would be really scary is if it only looks at me if I get close enough to it. So now you've got like a game of what's the time, Mr. Wolf, essentially. So let's go over here. Yeah, so that's quite creepy. Anyway, this wasn't a tutorial on making creepy things. This was a tutorial on vector math. So what we're doing here is we're using the Lua API to change the direction that the robot is facing. And by passing in a vector, and it doesn't need to be a normalized vector, which we'll get onto in a minute. It can just be any vector. It will then use that description of whatever that line is to point in that direction. So that is worth learning, because then you can get things to look at you or look away from you. If I wanted something to look away from me, I could literally inverse that, so minus it. Wait. Oh, minusing makes it look at me, and then positive of that. That's interesting. Positive of that makes it look away. Yes, that's the back. That's the back of the robot. Okay. So to make a robot look at you, it's actually minus that. That's cool. Now, what if it also moved? So we can do that. We can make it move. We could do self.properties.rotobo, and we can set velocity. Let's make the velocity. Let's just start by making the velocity this vector. That might be because okay, so it's moving away. So to make it move towards me, I would, again, just subtract that. So now the robot looks at me and constantly moves towards me, just by using that vector, because it knows the direction to go in. So now I've made a homing robot. Admittedly, it floats, but that's okay. We can do that. We can set that velocity, but we can do more. We can do more than that. We can also do let's put a baseball in here. Let's put one there. And I'm just going to stop this from moving towards me all the time. Let's get my baseball reference here. So this is the robot stuff. Let me just comment that. And then here, and that is in there. And here is going to be the baseball. And let's do the same thing we were doing with the baseball, except that. We've got the user position already, so we don't need that. Let's get baseball position. and that's going to be the baseball. Vector user baseball is the baseball position minus the user position. Okay, so with this baseball, one thing I wanted to do here is if I turn physics on and then let's just get the baseball and let's shoot it towards us. So we're going to do add impulse and put that vector in. That's all okay. So let's try that. We didn't attach the baseball to the code. Let's just rename that baseball. I've got a feeling I need to do this again. There we go. So the baseball is now, it's a slightly different type of homing because the baseball is now using, rather than using the vector as the velocity, which is an exact amount that its speed is, and it's being set every tick, it's now adding force every tick depending on its relationship to the player. So one of the problems with this is that the further away the baseball is, the more velocity it's going to attach. So the stronger it's going to come back to us. Now that's fine if you want that, but we can actually do something called normalization to stop that happening so that the force is always the same. And we can actually normalize the robot so that the robot's speed is always the same rather than being faster if it's further away. So let's normalize things. So here I'm going to do normalized vector user baseball equals vector user baseball normalize. And let's just output what that looks like. Let's just output, in fact, before we do that, let's output what this vector up here looks like. Normalized vector AB. Just so that you can see what this is doing. I will maintain consistency. So before, the numbers were describing the line, fine. They were describing it in terms of its size as well as its angles. Normalizing it means that you've now divided the entire line by its largest side, so its largest distance, which means that actually you've divided the line by its total distance, which means that now we have x and y and z as percentages. So they are numbers between 0 and 1. So they only talk about direction and they have no idea about the distance between them. Now that's really useful for another reason. So we can, now that we know that we can normalize things, and we can use that, we know that this number is now, this vector now consists of 3 numbers that are all between 0 and 1. And we can actually use that and we can scale that vector. So we can multiply it by a number. Let's multiply it by 100, so that now the impulse that we're adding every tick will be a number between 0 and 100 in each direction, which means that it will always be applied 100 in total. Remember, that's the total length of. But notice now it's a lot calmer. It's a much calmer baseball. And I can make it much more aggressive by making this number much bigger. So I can do, so now I've got a very fast moving baseball, which is orbiting me. That's quite interesting. So let's tweak that number a little bit. now that the number is consistently the same, where's it gone? So this was the calm baseball at 100. So the baseball will, because it's using forces rather than velocity, that means we're changing, essentially we're changing the acceleration rather than the velocity. And you can see now I've created an orbiting baseball, which is kind of cool. This is when you can use these vectors to create an entire working model of our solar system, if you wanted to. Just by using vectors and then positioning everything incredibly carefully. So that's normalizing things. If you wanted to take this even further, you could make the robot, if you get too close to it, you could make it look away from you, and let's make it vector user robot. Let's normalize that vector there, and let's move it away from me at a consistent speed of 100. Set velocity, yeah, something like that. So that baseball is going to be following me around. That's fine. Go over to this robot, look away, and move away from me. It's like, but only if I'm less than 500. That's quite interesting. Maybe we can make the robot. So you can play with these. I could go on all day about using these vectors, but you can see once you get the relationship between 2 points in a vector, you can use that vector in lots of different ways. You can change the velocity, you can add forces, you can rotate things, and then you can normalize that vector and do even more interesting things by scaling a normalized vector and manipulating that. So hopefully you've seen that some of the relationship between a vector that describes a position, a vector that describes a line, and then once you've got the line, you can do all of those interesting things. We haven't really touched on something that is also working behind the scenes in this game engine, which is these are Cartesian coordinates. So Cartesian coordinates is where you've got a specific position in the game world. But what you can also find quite useful is converting these Cartesian coordinates into polar coordinates, which is where you're now talking about the arcs that are going on inside a sphere and the position things are facing, the direction things are facing. So that is something I'm looking at doing in the future, where we talk about Cartesian and polar coordinate systems and why they are both useful in game development. But hopefully you found the vectors thing kind of useful, and hopefully you can now go and make some homing missiles, some proximity mines, and all sorts of stuff like that. Now that you have some further understanding of vectors. Like always, if you have any feedback for me on this tutorial, or if you get stuck and need some help, then please join the Discord for Crayta, or get in touch with Crayta on Twitter or something like that, and we will help you get to the bottom of any of those problems. And let me know if you do some cool stuff with vectors, because I'm really interested. I hope you have enjoyed this tutorial and have a great time in Crayta. I look forward to seeing you in the game.